Welcome. In this session in linear data analysis, we'll explore one relation between projection problems, which we've been looking at in this lecture, and a related problem, which is a linear equation. Suppose that we're given two linearly independent data vectors, A1 and A2, and that means that they're not scalar multiples of each other. Let's restrict them to size 3 for now. If we combine those, then if we gather them, then we get a matrix with 3 rows and 2 columns. And we then, suppose, are given a vector C, and it is also of size 3. Well, can we formulate a linear equation? Can we say that AW equals C? And the answer is, it depends. And what it depends on is this linear equation will have a solution if and only if C is in the column space of the data matrix A. And if it has any component that's in the orthogonal complement, then this will not have an exact solution. And that relates closely to the projection. That is, what we were trying to do was we were trying to project a vector C into the column space of this matrix. We were thinking of it as a vector space. Now, in matrix terms, we can think of this as a projection problem. How can we project C into the column space of a matrix, and what W's will do that? When we write this out term by term, it becomes clearer that here we have a 3 vector, here we have a 3 vector, here we have a 3 vector, and so we have 3 equations and 2 unknowns, and that's overdetermined. So it's unlikely that that will have an exact solution. So what can we do? Well, if we use the normal equation, so let's recall that the normal equation is A transpose A times W equals A transpose C. We derived this for the purposes of projection, but that is exactly applicable to an overdetermined linear equation. So can we solve this using the normal equation? Well, not exactly. We can't solve it, but we can approximately solve it. And this idea of approximate solutions is a very powerful one in linear data analysis. So, what have we learned in this lecture? We're now able to formulate a projection problem. Given a set of basis vectors and a new vector, we can formulate this as a projection problem of finding the nearest vector in this vector space to this new vector. We can solve for the weight vector W that performs that projection. We can find the vector that is the projection, and if required, we can find the error vector. And we can do all of this using the techniques that we've developed in this lecture.